Okay, we're back with another video. We're going to be doing vertical stretches and shrinks this time. And as you guessed, we're going to start in Desmos, okay, and then I'll show you some examples on the boards. So the next step, we're going to be talking about this A value here. Get excited, and here we go.
All right, back in Desmos, and we got our equations, our parent functions, this time with an A value out in front. Again, the A value not in a group with the X, but kind of outside of it. And I want you to see what happens here when I manipulate this A value. Okay, so right now it's 1, right? So it's saying 1 times this, so that's not really changing the shape, okay? But watch what happens when I change this. Okay, so A is 1. Look at the graph as I make it A value bigger. Now it's 2. Make it bigger. The A value is 3. Do you see what's happening? It is making this curve skinnier. Okay, so when we have an A value, I call it a multiplier. When we have an A value, that's what actually changes this shape. Okay, it's not changing it totally, but it's making it, skinnier. And if you get less than 1, you see that it is making it wider and wider, right? So that happens too. Okay, and again, just want to show you that for all parent functions, or most of them. So we have absolute value, A is 1, so that's the standard one. If I make it bigger, you see that V is getting taller and taller. And then you make the A value less than 1, and that V kind of gets wider and fatter, okay? And then same with square root. Square root's a little different, okay? So you make it bigger, it just makes this curve a little taller when you make the A value bigger, right? Just kind of makes it a taller curve. And if you make it less than 1, closer to just like a horizontal line. And then cube root is similar. Cube root, when it's 1, that's the standard. But then we make it smaller than 1, kind of closer to 0, flattens it out a little bit. Then we make it bigger, makes the curve bigger. So this definitely changes things a little bit. It's probably the most complicated of our transformations that we do. So we'll do some examples here of that, and hopefully you'll get the idea. But I just wanted you to see that first here in Desmos. Good times.
Okay, hopefully you're able to see in Desmos just what exactly this A value does, right? So this is where we're actually going to be changing the shape of the graphs that we're dealing with, okay? And so it's changed based on how big or small these numbers are, right? So like you saw that the bigger it is, like 2 or 3, it almost makes it taller. So that's what we call a vertical stretch. So if it's like 2 or more, right, the higher the number gets, and same with negatives, but that's negative deals with something else. But the higher the number is, or the higher the digit is, the more vertically stretched that it is. Okay, so it makes it like taller. Okay, whereas a shrink would be the opposite, and that's where if it's like a fraction, 1/2, or 1/3 or whatever, it kind of takes it and it pushes it down. Okay, number 1, y equals 3x squared. So the parent function there, again, starting the same way as we always have. That is a quadratic parent function, okay? So you're going to draw that. At this point, you should be pretty good at drawing these parent functions. There we are, okay? And a quadratic, that is, what's happening to it? Well, the only change from that normal original parent function equation is that it's being multiplied by 3. So I like to say that's a 3 times multiplier. Okay, you can write it out like that. So you wouldn't just say a vertical, you can call that a vertical stretch, because it's important that we quantify just how much it's being stretched by. And that number kind of determines that. Let's sketch out what this is going to look like here. Okay, so I have no other like shift to the right or to the left or up and down, so that origin point remains right in the middle. But basically, right, a vertical stretch, meaning the y values are going to be 3 times higher than they normally were, right? So instead of counting up 1 and over 1 in both directions, I'm going to times that amount by 3. So instead of going up 1 and over 1, I'm going to go up 3, 1, 2, 3, and over 1. The x value amount, the amount side to side remains the same, but the amount that I move up is stretched by what this multiplier is. So up 3 over 1 to both sides. And then the next points in my parent function were up 4 and over 2. So I'm going to move, again, times that amount by 3. So instead of going up 4, I would go up 12, because 4 times 3 is 12. So up 4, 5, 6, 7, 8, 9, 10. I'm going to move up off my graph a little bit, 11 and 12. Just pretend those points are there. Up 12 over 2. So that'd be like there and there. So again, it stretches it, and it makes sense that it's going a lot, we're counting a lot further up because that's what a stretch does. It's like we're stretching this graph out vertically. So that's what that graph would look like, all stretched out. Domain and range still, we're dealing with those. Domain, again, like all graphs, you should notice at this point, all real numbers because it will expand wider and wider forever. And that's what's crazy about infinity. Even though there's a times 3 multiplier, and even though this is stretched, this will eventually get out wider and wider till it gets to positive and negative infinity on the x and y axis. So crazy. It's still all real numbers. Range is not all real numbers because it doesn't go up and down forever. Okay, it goes up forever, but at the lowest point it ever gets is 0. Okay, 0 on the y-axis. So we'd say y greater than or equal to 0 is my range. All right. Looking at number 2 here, y equals 2 times the square root of x. So square root is my parent function. Okay, let me sketch that guy out here. Okay. Okay, there's like my cannonball shot there, my parent function of a square root graph, okay? And then I'm going to shift this, right, or I'm going to stretch this, right? It's being multiplied by 2 out in front. So that means it's going to be, again, you can write 2 times multiplier, or you can write, again, that results in a vertical stretch, okay? A vertical stretch. And so again, it's not, no other shifts are happening, so we're going to remain right at that origin point. But then again, from where we'd normally count, the horizontal, the side-to-side counting remains the same. So this first point after the origin point is still going to be right 1, but instead of moving up 1, I'm going to move up 1, 2. Again, not up 3 like this one, because this one had times 3 in the front. Times 2 because that's the amount that the y values are getting multiplied by or expanded by. This point was over 4 up 2. Okay. Again, I multiply the vertical amount that I moved up by 2. So instead of moving over 4 up 2, I'm going to move over the same amount, but times 2 of what I moved up before. So up 4 over 4 right here. That's what that stretch does. Same with this one here. I was over 9, and it's going to remain over 9, but instead of moving up 3, I times that vertical amount by 2, so I'm going to move up 6. That's what the function would look like, okay? Just not like it's still that similar shape, just kind of pushed up a little bit. All right, and then domain and range for this one. Domain and range, they actually do not change from what the parent functions would be because you see that it's going in the same direction, and that origin point kind of serves as the lowest x value and the lowest y value it ever touches. So both of these would be x is greater than or equal to 0 and y is greater than or equal to 0, okay? Because again, the lowest x value it ever gets to is 0, the lowest y value it ever gets to is 0. Goes to all the positives after that. Okay, let me erase these. We're going to do 2 more examples and then more examples in another video. So here we go. Alrighty, we've got 3 and 4 drawn up here. So y equals 1/2 times the absolute value of x. Okay, and again, that's characteristic of the a value, that it's outside of a group with the x like this. So again, but first we start with our parent function, which is absolute value. And again, drawing that, start in the middle and then make your V shape like so. Okay, so then I look at my equation. I think, okay, what are the shifts or transformations that are going to happen based on the equation? And all that I have that is different from the original parent function is this 1/2 multiplier. And again, that, you can write that, 1/2 multiplier. And again, that's going to result in a vertical shrink, or it's like you're at the top and bottom of this and you're pushing it down. Okay, so it's going to be a little bit fatter, I like to call it too. And that's it. That's the only transformation that's happening. So then drawing this out, what it looks like, okay, again, my origin point remains the same, 0, 0. But then for this one, right, for a 2 times multiplier, I doubled the amount that I moved up vertically for each point, okay? Multiplying by 1/2 just does the opposite. 1/2 means I'm counting half of what I originally would have counted when I move up. Okay, so this one's going to be, you might have to zoom in and look closely here. Okay, so in this first point here to the right, I move right 1 up 1. Okay, for the new point for this function, I'm going to move right 1 and only up 1/2 because I'm moving up half the distance that I did from the parent function to that point. Okay, and the same goes for the other side. So left 1, instead of left 1 up 1 to get to this point, left 1 up 1/2. Okay, so that is where that point is. Okay, this is the same thing with these two. Again, normally I moved up 2 and over 2 to both sides. Again, I cut in half the distance that I moved up. Okay, so instead of moving up 2, I only move up 1, but the horizontal stays the same. So I still move right 2 and left 2, but instead of moving up 2, I only move up 1 from the origin. So those points are going to be right there. And so this graph would kind of look like that. So you see it's like somebody pushed that down a little bit, made it a little bit fatter, a little bit wider. And so that's the difference between a 1/2 or a fraction or a number lower than 1 and a stretch of 2 or more. Okay. Again, as always, domain and range, they actually don't change here. Domain will be all real numbers. Range, again, it only goes down to 0 and all the y values above that. So y greater than or equal to 0. All right, number 4. Look at this guy, crazy. And again, this is a taste of kind of all the different transformations that we can have within one equation. Crazy. So this says y equals 2 times the group x minus 3 cubed minus 5. Wow. So again, same process though, no matter how complicated it is, same process. Okay. So my parent function is a cubic based on that 3 exponent. So I draw that sucker up here. So again, -1, -1, 0, 0, 1, 1, and then 2, 8, because it's cubic, so it's taller, and then -2, -8. Okay, so there's my original parent function, and then I have to analyze what are my different transformations that are happening based on how this equation is. Okay, and I got 3 of them. Okay, I have this -3 that is inside, so that'd be the h value. So this -3 is a horizontal shift of right 3. Next, this -5 is a k value, so that's a vertical shift, and that would be down 5. So that's where my origin's moving, right 5, down 5, or right 3, down 5. And then I have this 2 times multiplier on the outside. So that is a 2 times multiplier, which means I'm taking a vertical stretch. Okay, so there you have it. Those are my 3 transformations, and so let me draw that out, what that's going to look like. So origin point, right 3 and down 5. So I take the origin, I move right 3, down 5. There it is. There's my origin point. And so again, what can be helpful here too is sketching, like kind of doing it a step-by-step process. So we took care of these by moving the origin. We're going to make my shape based on that. But if you need to, it can be helpful here to just draw little mini points of where the original shape, right? If it was not stretched, how it would look. Okay, so I go right, down 1, left 1, up 1, right 1. That's that shape. But then I count up 1, 2, 3, 4, 5, 6, 7, 8, right 2. Again, this isn't what my actual graph's going to look like with this 2 here, but I'm just drawing it so that we can refer to it. And then so down 8, I can't really fit it, but it would be like here. So then from there, again, I am going to double, because of this 2 multiplier, I'm going to double the vertical amount that I'm going to count to where these points would actually go. Okay, and I'm not going to be able to fit all of them because doubling it's going to move some of them off the graph. Okay, so I would move, instead of up 1, right 1, I'm going to move up 2 and right 1. Again, just doubling that vertical amount because of that multiplier. So that's where this actual point's going to go. This one, normally I go down 1, left 1 to get there, but instead I'm going to go down 2 and left 1. Okay, so that's where that's going to go. So again, I'm stretching this vertically, making it longer and taller. Now, for these, again, I move up a whole bunch to get to them normally. So I'm going to have to move up even more, right? I'm doubling that amount. So normally I move up 8 and right 2. So yes, I would have to move up 16. So let me see if I can fit that. 15, 16. So I can. It's just barely off my graph. So up 16, but again, that horizontal amount stays the same. So up 16, it's a whole bunch, and right 2 from my origin point. Okay. And then this one, it was off the graph before, so I'm definitely not going to be able to fit it. So we'll just ignore that one. Okay. But my graph will look like that. Okay. Domain and range. Domain and range, you might have guessed it, they do not change. All real numbers for both. Because there is no limit to how far these can extend left to right and up and down.